Michael Ionescu in Australia to do this on YPCO, and we were successful. In parallel, some other guys, both in Japan and in the US, did some similar things. Next one was to do this nano island several times, to do some sort of quasi-superlattices. So we have incomplete layers of a secondary material, so we grow on the texture substrate, one layer of YPCO, then incomplete layer of nano islands of something, repeat with YPCO, repeat with nano islands, and so on and so on. And this is quasi-multilayers of quasi-superlattices. First published one was by Tim Hogan, which used to work, I think, still working for US Air Force Laboratory for research. And later on, the group of Bernard Holzapfel in Dresden tried to do the same thing. And the third one is to use nanostructured targets, in which we have a target which have secondary phase nano inclusions, and we use laser deposition, and we have superconducting films in which we have find again the nano islands from the target. The first publication was with Judy Driscoll, which is from Cambridge, but in that time he used to spend every summer 2 months in Los Alamos. Later on, at Oak Ridge Laboratory, in increasing a little bit the temperature and decreasing the frequency of the laser shots, so giving more time to those nanoparticles to self-assemble, those nano islands were shown to be able to self-assemble into nanorods, so to create some sort of correlated C-axis extending effects. Okay, several types of materials have been used now for substrate decoration: silver, magnesium oxide, yttrium oxide, silicium oxide, iridium, gold, palladium, lanthanonickelates. For the quasi-superior approach, the green phase, E223, E2 zirconia, then different compounds from transition metals, and silver against gold, palladium, lanthannickel oxide, praseodymium, barium copper oxide, and non-superconductivity barium copper oxide. For impurity addition to targets, the first one was barium zirconate. Of course, many groups tried that. Then barium niobate, barium tin oxide, then tanthalates, again Judith, double perovskites, and the 2411 phase. So you can also try different combinations of many impurities to create a very, very complex peeling landscape in your material. Okay, we discussed about the rationality strength of peeling centers. Okay, so I will show you some peeling centers films obtained by PLD. This was my project in Birmingham. This is a typical PLD chamber. I don't think I have to explain too much about that. So you have to shut the laser at 45 degrees on the target. You need to have a controlled oxygen there, atmosphere, background gas. This is the plume. Heating the substrate. You need to correlate all the time the power of the laser, the frequency of the laser, substrate temperature to get the good results. So this is an image during the deposition. This is how it looks. Okay, so substrate decoration. This is distribution of silver nanoparticles at 400 degrees Celsius, about 50 laser pulses. We have seen that using these conditions, we get the best results in terms of improving clinical current in our case. And this is roughly how 1 micrometer thick film is improved by using substrate decoration. Now, if you look in the literature, you will see a lot of nice large values of clinical current densities for various films with artificial peeling centers. In my project, I tried something else. I tried to maximize not clinical current density, but the critical current. Because when you have a tape, the thickness of the superconducting material is a very small part of it. The largest part is the metallic substrate and then the buffer layers and so on and so on. So what we need to do is to increase for practical applications, not clinical current density, but critical current. So what we try to do is to grow much thicker films without too much decrease in critical current density. So what you have seen here, you will see here are films which are much thicker than the films which are reported by other groups, which are usually with a thickness which allows them to have the optimum critical current density, and that thickness is about 400-500 nanometers. Okay, another important thing with silver is that silver nanodots promote some sort of columnar growth of yttrium barium copper oxide or silver nanodots. So you can see here a cross-sectional AFM. So what we break a film and look at the edge using atomic format microscopy. So here is the substrate, so to pattern it, and here is YBCO for a normal film without anything. But if we put nano islands on the substrate, we can see both for gold nanodots and silver nanodots that the YBCO doesn't grow like this. It grows in the shape of some sort of columns. Why is this important? Because on the edge of this column, that edge of the column are very good two-dimensional pinning centers. So these surfaces here can accommodate a lot of flux lines. So by using only this thing, we show that we improved a lot critical current in this case. If we do quasi-multi-layers, so we repeat these things with silver several times. So this is, if we do just substrate decoration, we repeat it twice, 3 times, 4 times. So for 4 times, you will see that we have a film of 6 micrometer thick. And in comparison here, a pure YBCO of 2 micrometer thick, these stars. In terms of JC, the one with just 2 has the largest one. The thicker one has a smaller JC, but if we plot them in terms of critical current as amps per centimeter width, you see all these quasi-multi-layers are much better than the 2 micrometer thick pure YBCO. Here are some types of defects which we have seen using transmission electron microscopy. So here is a large E2 precipitate. Here you can see the copper oxygen 2 plates. TM image showing correlated C-axis defects. Misorientation in the boundary area. Nanoparticles around here. Here at the substrates you see very nice boundary between the substrate and the YBCO film, so we have very good quality growth. Then columns structure from the substrate, another columnar structure, nanoscale particles inside, a lot of elemental mapping to these defects. We try some other types of quasi-multi-layer films, for example, praseodymium barium copper oxide, which is a non-superconducting material, and lithium barium copper oxide. Again, we had an improvement. Some images of defects for this type of nanostructures. Now, one of the best results, as I said, is obtained if we have also the target which is doped with a few percent of secondary phase nano inclusions. And in our project, we have used the barium zirconate doped YBCO. And we also moved to using this target in the multi-layer architecture. So if we deposit at quite, well, not low temperature, but the temperature we used before, 780 degrees Celsius, and the frequency of laser shots of 5-6 hertz, we can see a lot of these nano islands of barium zirconate. Here. But if we use the results which were first reported by Boris Mayorov, also from Los Alamos, in which he showed that if you increase the temperature and reduce the rate of the laser shots, you have a much higher density of these correlated C-axis defects. We have these nice nanorods. We also have some nanoparticles inside. Again, some elemental mapping, and I'll stay with you. And you see here, this is something very, very ugly. But this is very, very good for pinning, because we have all types of defects, we have also some splay defects, so not all of them are parallel. If you have all the defects parallel, columnar defect, you have the vortices will form a Bose glass, and in a Bose glass, if you don't have any type of defects, you will have a double kink formation, and because of the interaction between those two loops, the double kink will extend, and the vortex will move itself to another pinning center. So, if you do not have other types of pinning center, to have only vertically aligned C-axis columnar defect is not good. So you see here, this pinning landscapes provides a lot of different types of pinning centers, which is very good. I'm showing you a lot more images of these to see how important the pinning landscape is, and to have different types of pinning centers. You see some of the nanorods are very long. You have also stacking folds there. And if we combine barium zirconate with multi-layer using silver, we got the best results which we have obtained in that 4 years of ongoing project. So you see all these kind of things are pinning centers, and we will go soon to see some sort of results. Okay, substrate, you see defects there. Now, one quite important thing which happens between silver and barium zirconate. So barium zirconate will make these nanorods, which in my case are quite splayed, so they are not perfectly aligned on the C-axis. And as I said before, silver promotes a columnar growth of YDCO. So these white columns are columns of YDCO, and they are entangled with barium zirconate nanorods. These black lines are the lines we draw just to show you where the YDCO columns are. And you see this nanorod which goes beyond this column. So this entanglement allowed us to obtain a lot of nice things in terms of critical current and anisotropy. And these are some last images in which we have used also some multi-layer growth, using also some few nanometers of titanate for an ongoing project of trying to make some sort of coil, making multi-turn, multi-layer in situ coils with a friend working in England at 3Cs, Evan of Meyer, which has started a spin-off company. Okay, so this was about pinning in YDCO films and modular superconductors. As I said, pinning in MgB2, don't miss the talk of René. Don't miss the talk. So MgB2 wires are produced by various variants, but all of them are powder in tube processed, so you just pack the powder in the tube and you process it like a normal powder metallurgy. And again here you can use phase additions for the initial state. Carbon doping was very useful. Amorphous carbon nanodiamond, carbon nanotubes, different types of other atoms, and so on and so on. Nanosilicon, silicon carbon nanoparticles up to 30-40 mole, bio-rich phase, magnesium to silicon secondary phase, oxygen and silicon containing matrix, silicon and oil liquid precursor. So a lot of this work has also been done by Professor Doe from in Australia. I don't know if is he coming this conference?
One guy coming from there.
From his group, okay. Alexei Pan? No.
Hussein.
Hussein, okay. Okay, and about melt texture rare barium copper oxide, so these big chunks of melt texture into barium oxide, which can be used in aerospace for gyroscopes and other things, for levitation. Elemental to barium copper oxide. They are very light rare earths. So there are many ways in which which you can also increase peeling centers and trap fields up to 5-6 Tesla in such melted relative to barium copper oxide. Now, a friend of mine from Cambridge, David Cardwell, has another type of phase, and he managed to use a new technique in which you don't have one seed, you have multiple seeds in the growth, and he can manage to make big single grain rare earth barium copper oxide with his 211 nano inclusions, and he has a very nice lucrative contract with Boeing for developing gyroscopes. If you are interested in this, just look of his recent works. Okay, I think I'm stopping now. Please, questions. Yes.
Actually, I have two questions. But first, about you showed multi-layer structure with YBCO and silver dot nanoparticles. Yes. Yes.
Okay.
This one.
Yeah.
I wonder how did you manage to deposit STO on the bottom YBCO layer, because it includes some silver nanoparticles, right? So in the multi-layer deposition structure, so if you deposit STO on silver dot YBCO.
No, look here. What I have structural titanium substrate on which I put silver nano islands.
Yes.
Then I grow YBCO, and that YBCO is from a target which has barium zirconate. And then I grow strontium titanate, and it grows okay. I don't put any more silver.
I see, but my question is, what happens to silver particles in the bottom layer while you deposit STO? Because it requires some high temperature process. So I wonder if...
What happens to the silver?
Yeah.
Now, if you look at the quantity of silver, it's very, very small.
Yes.
So the silver nano islands, they do not stay there. They will diffuse. But during that time,
this is what you want.
silver acts like a catalyst for doing two things: promoting columnar growth, and secondly, allowing us to grow thicker films without a very drastic decrease in critical current density. So if you look at the cross-section with the best microscope possible, you will not find a droplet of silver. Silver is diffused all over the place, but during that diffusion time, silver has done its job.
Oh, thank you.
You said you have a second question.
Yes, but that was about, from your beginning of your talk, you showed something about magnetic flux quantization.
Yeah.
So, and then you mentioned about Bose-Einstein condensate. So, what I wondered, if flux quantization is experimental evidence of the Bose-Einstein condensate.
No.
Because,
No.
because we know that if there's Bose-Einstein statistics and superconductivity. So superconductivity is kind of a condensation. But if it is experimental evidence of Bose-Einstein condensate, and how they
in superconductivity, you might have, for example, non-apicosal vortices. You might have giant vortex. You might have the so-called pearl vortex. They are totally different in terms of topology. Giant vortex can have more than one flux. Right? In multi-component superconductors, which are now in fashion because of the first MgB2, then peptides, and then chalcogenides, when you have a multi-component condensate, you might have non-centrosymmetric vortices. You might have also fractional vortex, which are glued by Yeah, I miss the word now. Solitron.